Let's get started with lecture 15. So we're continuing the discussion of traveling waves. We're focusing on one-dimensional waves, particularly waves on a string. These are transverse waves that just travel along a string or a rope that's under tension in one direction. So last time we talked about two different pictures of thinking about waves on a string. So one was the snapshot picture or snapshot figures, or snapshot graphs, let's say. So these were the displacement pattern for different x's, fixed time. So let's say we call that d sub t for that fixed time of x. It's a function of x for fixed time. And we had the history graph, which is again a cross-section of this general two-dimensional function, fixed x, as a function of time. And we talked about how to visually extract one from the other. For example, get the history graph from a snapshot graph by just translating the snapshot graph forward as time goes on, and then reading off the displacement at one particular point. So in particular, we found this relationship. We found that, so let's say this is maybe a particular snapshot. We found that if we focus, let's say, on this particular point and we want to get its history graph, let's say that's the snapshot at t equals 0, then we just kind of reflect these, right? So then we have, as a function of t, our displacement somehow looks a reflection of that. Goes down, goes up, has a bigger bump, etc. And then here, of course, the x-axis or the horizontal axis is length. Here, the horizontal axis is time. And the distances are related by the speed of wave propagation. So if, for instance, here, or let's say we pick a particular point, let's say that's t, and then it comes from a point on this graph that's some distance away from this point, right? So the displacement that here at time t will be the displacement a distance x back, which is given by x by v times t, right? So this length is v times t because this whole pattern is shifting forward with constant velocity v, and after a time t, that's the distance that it has moved. So we found that if this is, for example, d0 of x at time t equals 0, then in general d of x and t becomes d naught of x minus vt. In the previous lecture, instead of talking about the displacement or the snapshot at t equals 0, I started discussing a more general case at some arbitrary time t0. If we have that, what we can say, but then I wrote the result for having the snapshot for t equals 0. So let's discuss that a little bit. So if that's not t equals 0, let's say that's some arbitrary time t naught, So let's say if d naught of x is d of x and some given time, well, it's just the same story, except we have to think about the time that has passed since that time. So then d of x and t simply becomes d naught of x minus v times t minus t naught, the time that has passed. Right, and that's just fixed by the boundary conditions, right? So if you put, for example, t equals 0, you just get d naught of x, which is by definition d of x and t equals 0. Here, if I put t equal t naught, I get d naught of x, right? Because t minus t naught becomes 0. And d naught of x is by definition the displacement as a function of x for t naught. Okay. So then we practiced a little bit with just localized pulses that travel along the rope. And then we talked about sinusoidal waves. So, for example, one way to generate them is we take one end of the string and just, as a simple harmonic oscillator, move it up and down as a function of time. And we argued, well, that can generate a sinusoidal wave that propagates along the string. And in both snapshot figures and history graphs, it looks like a sine wave. But the period is related to wavelength, the distance between two consecutive peaks in the snapshot graph, right? So if we have snapshot that looks like this, maybe, right? And that's the wavelength lambda. And if you have a history graph, that again, depending on what point we want to pick. So let's say we pick this point, for example, and then it will see these displacements that are behind it. So it will look something like this. Again, the periodicity of this is the period of the oscillations at that one point, and lambda is equal to vt for the same reason that the distances shifted are v times t. And if your shift is one full cycle, that corresponds to one wavelength here and corresponds to one period in the history graph. So we talked about these. We derived the general equation for these sinusoidal waves. So we derived the equation d of x and t is some amplitude, which is the same, right? We would see the maximum displacement to be the same in both snapshot graphs and history graphs, and then that multiplies sine of kx minus omega t plus some phase constant, and k was 2 pi over lambda, omega was 2 pi over t. We talked also a little bit about the physical velocities of the different pieces of this rope that undergo simple harmonic motion in the vertical transverse direction, and therefore their history graph looks like this, looks similar. So to get that velocity, we just fix x if we're looking at some particular point, and then take the derivative of this with respect to time. So velocity of pieces of the rope, we found it to be v of x and t to be minus a omega cosine kx minus omega t plus phi naught. Okay, so that's a review of what we covered last time. So far we talked about waves propagating in one medium, right? So we just had one rope with one propagation speed. So basically it was one rope. If it's one rope, it has the same tension. But we also assume that it has the same linear mass density, so the speed of propagation is the same. We can have interfaces between different mediums or different ropes. So here is an example where you have string 1 with some linear mass density. It seems it has a smaller linear mass density. And then it's just connected to another string which is thicker, so it presumably has a higher mass density. So we want to see how waves behave as they go across interfaces between different uniform systems or uniform strings. So you have this lightweight string and there's a wave that's traveling, so maybe we take the left end of this and move it up and down, so we generate this wave that's traveling. So let's say that's the leading edge and it's just approaching this other medium. So what happens? So which one of these statements is true? So pause the video, think a little bit about this, and then we come back and talk about it. So the wave in the rope, in the lightweight rope on the left, is characterized by its wavelength, lambda, and its frequency, f. So we call them lambda 1 and f1, for example. They correspond to string 1. Now, so first let's think about the frequency, right? The frequency is how many oscillations the source is putting into this system per unit time, right? So it's just a property of the source that's generating these ups and downs, right? These pulses. So there is no reason it should change as you go across that interface. It's really a property of the source. Another way to think about it is this point here, right, which belongs to both, let's say, the left string, string 1, and the right string, string 2. Well, it's moving up and down, right, in some way. It's performing some kind of oscillatory motion, which has a frequency. Now, because it's part of string 1, it must have the frequency of oscillations of string 1. But it's also part of string 2, right? So the endpoint of string 1 and the endpoint of string 2 at the point of contact are moving together. So the endpoint of string 2 will have, again, oscillatory motion with the same frequency, just because these two things are connected and are moving together. So, and then, this endpoint, you can think of it as some source for the next string, for string 2. And then again, these pulses propagate, but the frequency will be the same. Okay, so if the frequency is the same, then what about the wavelength? So what happens as we go from string 1 to string 2? What happens to the speed, right? Remember, the speed was the square root of tension over linear mass density. So if the linear mass density goes up, as you enter string 2, its speed speed of wave propagation will go down, right? It's heavier, it has more inertia, so waves propagate more slowly. Okay, so then what can we say? We know lambda is equal to Vt, and T is 1 over F, so that's V over F. So if V goes down, right, V gets smaller, V2, let's say, so F1, let's say, is equal to F2, and V2 we establish is smaller than V1, right, because V is the square root of tension over mu, so V1 is tension over mu1 square root, V2 is the square root of tension over mu2, and tension is the same, mu2 is larger than mu1, so V2 must be smaller. So if the velocity or speed of wave propagation goes down, its wavelength must go down and the frequency does not change. So that's our correct answer. The wavelength gets smaller as you enter the new medium with a different speed for wave propagation, and the frequency remains the same. One way to think about it is that the frequency is just the property of the source that's putting in these number of oscillations per unit time into the system. Or you can think about the boundary condition at the point of contact, right? At this point, they're moving together. So if you look at the history graph of one point belonging to one string, it has the same frequency of the history graph of this point belonging to the other string. They're connected, they're moving together. So we can't have that if the frequencies are different. All right. One thing that's important to realize is that so as you have this wave incident on this interface where the speed changes, it's not that it only goes through. Some of it goes through and some of it gets reflected back, right? An extreme example is, suppose, that's a solid wall. Let's say the density is infinity. So nothing can go through if it's really, really heavy. You can't, you don't have enough energy to get it to move. So all of it gets reflected. So that's something that we'll discuss later in the next chapter. But before getting into the details of kind of what gets transmitted and what gets reflected as your incident on this interface, we can make these qualitative assertions about what happens to the frequency. It doesn't change, and what happens to the wavelength. Let's go into the other medium. All right, so let's continue our discussion. So this is a very good example, and so let's read it together, and then you can pause the video and work through this problem, and then we'll come back and work it out together. So we have a very long string. We know the linear mass density. It's stretched along the x-axis. We know the tension. And then at x equals 0, it is tied to a 100 hertz simple harmonic oscillator that vibrates perpendicular to the string with an amplitude of 2 millimeters. Okay. So the oscillator is at its maximum positive displacement at t equals 0. Okay. Then we want to write the displacement equation for the traveling wave on the string. And at t equals 5 milliseconds, find the string's displacement at a given point from on the string at a given point. That's a distance 2.7 meters from the oscillator. And the model is that this oscillator is generating a sinusoidal traveling wave, right? So the history graph for that point is a sinusoidal function of time. therefore the snapshots will be, again, sinusoidal functions of position, and we need to kind of match the displacements to the displacement of the oscillator at that point. All right, so take a piece of paper using our general equation for these traveling waves, try to find the solution here. All right, so here I just translated the information that was given in the problem into equations, right? So it said the linear mass density is 2 grams per meters, the tension is 5 newtons. And let's read the language here. Let's see what it says. So it says at x equals 0, it is tied to a 100 hertz simple harmonic oscillator. So that's the source, and then the frequency of the source is given. So that's the frequency of the oscillations that we put into the system, and that's the frequency of the waves, therefore, that propagate in our system. And then we also know the amplitude. So A, the amplitude is 2 millimeters. And then there's this piece of information about the initial condition. So we know that the oscillator is at its maximum positive displacement at t equal 0. All right? So that means, well, that's the frequency, that's the amplitude, 2 millimeters here. And then at t equals 0, we're focused at x equals 0. We know that the oscillator is at its maximum possible value. That's plus A, right? That's the amplitude with a positive sign. So that's all the information we have. So now let's see how far we can get. So we know the general form for some phase constant must be d of x and t, right? The displacement at position x at time t must be A, the amplitude, sine kx minus omega t plus some phase constant. Okay. Now, so what is omega? Omega is 2 pi times the frequency, right? So that we already know. It's 2 pi times 100, and that's in hertz, or 1 over seconds if you wish, or rads over seconds. So we know omega, so that's good. We know this number here. We need to know A, we need to know K, we need to know phi naught. A we know it's given to us directly, so A is, let's say, so 2 millimeters, that's 0.02, right? 2 over 1,000 of meters. Then what else do we know? So A is good, omega is good. What about K? So what was K? K was 2 pi over lambda, the wavelength. Well, what was lambda? Lambda was V times T, or V over F. So that becomes 2 pi V over F. And V goes upstairs, and that's 2 pi F over V. Okay? The speed of the propagation of our wave, and we know what that is. That's the square root of t over mu. We have all those numbers, so we're good with that as well. So that's 2 pi f, we know f, that's 100 hertz, over the square root of t over mu. So let me take that upstairs, and if we enter these numbers in the proper units, so let's again write that 2 pi times 100 times 2 grams per meter. So gram is again 0.002 this 2 over 1,000. And then the tension is 5 newtons, so that's the square root of 5. So that's going to be some number whose units are 1 over meters, right? Remember, k times x must be dimensionless, right? The argument of a sine is dimensionless. K is 2 pi over lambda. Lambda has dimensions of 1 over... Lambda has dimensions of meters. 1 over lambda has dimensions of 1 over meter. X has dimensions of length. All right, so we can calculate all of these numbers. So we're good with A, K, and omega. All right, so let's think about phi naught. So we know at x equals 0 and and t equals 0, the displacement is its maximum positive value, right? So plugging in x equals 0 and t equals 0 into this, we find A we know is d of 0 and 0, x equals 0 and t equals 0. And that's going to be A times sine, well, those two terms disappear because we're setting x and t to 0, sine of phi naught. Okay, so canceling out the a's, it means sine of phi naught is 1. Right, so thinking about the sine, if it's 1, if it's over here, then phi naught must be pi over 2, right? That's our angle. Okay, so we're now basically done, right? We know the general form of the equation, and we found all the numbers that appear in it. So then that's it. That's the answer. And if we want the displacement at some point and some time, we just plug in the numbers in this general form. All right, so let's take a look at the solution together. Yeah, that's the general form that we can write. So phi naught from the initial condition we know becomes pi over 2. Omega we can calculate because we know the frequency. The speed we can calculate, and then we know lambda, which is v over f, so we plug all of them in, and that's the answer. It's these numbers that we just found, so that's a known function of x and t. And then if we're interested in some particular point, we just put in the numbers. Okay, let's do one more example. So this is problem 1613. Problem number 13 of chapter 16. So it says the displacement for a wave traveling to the right is given by this equation. So d of x and t is 3.5 centimeters times sine of 2.7 times y minus 124 times t, where y and t are given in meters and seconds. And then it's asking, has 3 parts A, B, C, so it's asking determine the frequency, wavelength, and speed of this wave. Okay, so how can we do this? So what are the things that we know, right? So the numbers that are given to us, well, we know the amplitude is 3.5 centimeters, but the problem is not asking about that. So that the two other numbers that we have are k, the coefficient of this is y and t. X is just called y in this particular problem. So we know k is 2 pi over lambda, and that's 2.71 over meter, right? We can just read it off. What multiplies the distance is k. What multiplies the time is 2 pi over the period, or 2 pi times the frequency, so omega, So omega is 2 pi f, and that's 124. Again, the units are 1/2. All right, so we now have lambda and frequency, right, from these two equations. Just looking at our general equation and identifying these numbers, we find that lambda becomes 2 pi over 2.7. That's in meters, right? And then, so we have that. We also can easily find the frequency, which is 124 divided by 2 pi, and that's in 1/2, or that's in hertz also. They're the same thing. So the other thing that we're supposed to find is the speed of the wave, right? So we know that lambda is the speed times the period, which is also the same as 1/f. So therefore the speed, if you multiply both sides, becomes the product of lambda and f. And that's, the 2 pi's cancel out when we multiply, so that's going to be 124 divided by 2.7. That's meter per second. Yeah, so remember, it must be a function of distance minus v times t. So immediately that tells us that the ratio of the coefficient of t to the coefficient of distance is the speed of wave propagation. Okay, here's another example, again from the book. It's problem 47 of the end of the chapter. So that's the figure. So we have two strings tied together, and then we know the linear mass density of the first one is 2 grams per meter. For the second one is 4. They're different. It's 4 grams per meter. So then what's happening is the student grabs this knot, pulls it up, and lets it go. So then it generates a pulse that will travel into both strings in the two directions. And we want to see where the knot should be. What are L1 and L2 if the total length is 4 meters, so that the pulses that are generated at that point reach the two ends at the same time. Okay, so pause the video and think a little bit about this problem, and when you're ready, come back and we'll look at it together. All right, so first, what's different about the two strings? It's the linear mass density. The tension must be the same. They're connected, and they're not accelerating in the horizontal direction. So there must be the same tension throughout both of them. So they have some tension that's the same for both, but we don't know what it is. And they have these linear mass densities that we do know, they're given. So somehow the speed that the pulse propagates into these two strings, right, depends only on the tension and the linear mass density. And we want to find those two distances. So the pulse reaches the end or travels those distances at the same time, right? So if that's the case, what's the mathematical description of that? Well, suppose speed in string 1 is v1 and speed in string 2 is v2. Okay. So this is going to be tension divided by the square root mu1. This is going to be tension divided by square root mu2. And then we want L1 to be v1 times t, right? Because if the pulse reaches the walls at the same time, it means it took the same time t for both of them. So in one medium, it travels with speed v1, and covers a distance L1, in the other medium it travels with speed v2 and covers the length L2 over the same time. So okay, so these are the equations we can write, and we have this unknown time and we have this unknown tension. But maybe they don't matter, right? So let's just plug them in. So L1 is V1, let's put it in, square root T over square root mu1, let's say, times T. And L2 is square root capital T, the tension, over square root mu2 times T. So we see that if we divide these equations, these things that we don't know just go away. Right, and what we find is that L1 divided by L2, the capital T and the T cancels out, so this becomes square root mu2 over square root mu1. Okay, so yeah, so then we found a ratio L1, L2. So what is that ratio? So we know that mu2 is twice mu1. So that's square root 2 given the numbers that are given to us in this problem. String 2 is the heavier one, so it means things move, or pulses move more slowly. So L2 is smaller than L1, therefore. And then we have L1 plus L2 is 4 meters, right? That's just looking at the geometry. The total length is given to us, so that's L1 plus L2. And then we can solve for this, right? So the first equation gives us L1 is square root 2 times L2. So if I plug it in, I find square root 2 times L2 plus L2 is 4 meters. And therefore, I factor out the L2, so I get square root 2 plus 1 here. That's 4 meters. And then L2 becomes 4 over square root 2 plus 1, that's in meters, and L1 is square root 2 times that. So it's 4 times square root 2 over square root 2 plus 1, that's in meters. Okay, so here's another example. This is again problem 61 from the end of the chapter. So it says you have a string that has tension 5 newtons and it has a linear mass density of 5 grams per meter. And then there's a sinusoidal wave with amplitude 3 centimeters and lambda, or wavelength, equal 2 meters that travels along the string. So what is the maximum speed of a particle on the string? So pause the video and think about this problem for a few minutes, try to solve it, and then we come back and discuss it. All right, so I hope you managed to find the solution. So let's see what are the things we know, right? So we know the tension, we know the linear mass density, so we can immediately extract the speed that the wave travels along the speed at which the wave travels along the string. So we can find that. So let's say the velocity or speed of the wave, which is this constant and it's a property of the medium, namely a property of the tension and linear mass density. So that we can find. So that's going to be square root of 50, 5 grams per meter. That's 5 times, let's say, 10 to the minus 3 kilograms per meter. So what do we get here? So that becomes 5 cancels with 5. We get a 10 in the numerator, and then this goes upstairs. So it seems it's 10 to the 4. It's 1,000. The square root should be 100. And that's in meter per second. We put everything in the SI units here. Okay, we know lambda in meters. Okay, that's good. So we know lambda, we know the speed of the wave. And the problem is asking about the maximum speed of a particle on the string, right? So it's about the physical velocity or the physical speed of a piece of this rope, a particle that belongs to the string. So that's something that's changing as a function of time, right? Every little piece of this string is performing simple harmonic motion. It moves up and down. So what can we say? So the general equation again can be used here. So we know that d of x and t in general can be written as the amplitude, which is given to us again. It's 3 centimeters. So let's also write this. So we know amplitude is 0.03 meters times sine kx minus omega t plus some phase constant. All right, so what is the velocity of a piece of this rope? We just fix x, treat it as a constant, take the derivative with respect to time, right? So if you fix x, then this function of time is giving you the simple harmonic motion of one piece of the string at that x, right? At that distance from, let's say, some origin. So we can find the velocity to be, by taking the derivative, minus a omega cosine kx minus omega t plus phi. Okay, so as time goes on, and this we can be at any distance, but as time goes on, this cosine goes all the way, right? It experiences all different phases, so it will be fluctuating between -1 and 1. So the maximum speed is when the cosine is either +1 or -1. So it's going to be again a omega, right? We saw this also for a simple harmonic oscillator. It's basically the same thing, right? If you fix x, we can assume that kx is just part of this phase constant, so it's just cosine omega t plus something, or minus omega t plus something. Cosine of theta and minus theta are the same, so the sign really doesn't matter there. So that's the maximum speed. It's basically the product of the amplitude times omega times the angular frequency. Okay, so A we know, right? It's given to us directly. We know the amplitude. What about omega? How can we get it? Well, omega is 2 pi f, right? It's related to the frequency. So we don't have the frequency, but we have the wavelength and the speed of the wave. So we know that lambda times the frequency is the speed at which the wave is propagating. So from here, we find that f is lambda over this v. We call it what? We call it v wave rather than v wave here. So lambda, sorry, this velocity, this speed divided by lambda, right? We just divide both sides of this equation by lambda. So we know omega, right? That's going to be 2 pi 2 pi, the wave speed we calculated, divided by lambda. Right, so putting that together, we find finally that Vmax, the maximum physical speed of a piece of this rope or a point on this rope, is a 2 pi wave divided by lambda. All right, so putting in numbers, a is 3 centimeters, so that's 0.03 meters. 2 pi is 2 pi. The wave speed we calculated to be 100 meters per second. And lambda is given to us as 2 meters, right? So this again should be in meters per second. And yeah, so what's happening? So this becomes, just canceling out some numbers. 3 over 100 times 100 is 3. And then 2 cancels this 2, so it should be 3 pi meter per second. Okay, so that was a rather good exercise. We had to bring in many different pieces of what we learned about waves and harmonic oscillators together to solve this problem. A few points that very frequently cause confusion, and that's to some extent the consequence of the notation, is we have to be very careful not to mix the wave velocity, the horizontal velocity in the direction of the string at which the pulses or the waves travel, with the physical velocity of different pieces of the rope or the string that's perpendicular to the direction of propagation. I also, when I wrote this, I used frequency instead of the period. So that's also another confusing thing. Period is shown by capital T, tension is shown by capital T. And it's clear from the context what each of them are, but yeah, I mean, I've seen many students get confused by that. So it helps, like when we're doing this type of kinematic problems or periods and wave number and angular frequency, these things come in, maybe we can calculate just the wave speed using the tension, and then don't use the tension again. So I kind of numerically calculated this. All right. So I think that's a good place to stop.